Great. Thanks for having me here. So I think I should give a heads up that even though this is indeed titled Observational and Theoretical Outlook at the Epoch of Ionization, my talk is not so much going to be about the process of ionization itself. Rather, it's really going to focus on this type of experiments, these line intensity mapping experiments that will be looking towards this epoch. I'll talk a little bit about where current experiments stand, and I'll also talk a little bit about the theoretical outlook in terms of topics that are relevant to both forecasting and analysis. And I think maybe it's good to start with the name of the game, which is we really want to map large cosmic volumes. We do this with the initial condition of the universe, of course. We map the entire CMB across the whole sky quite explicitly. And then, of course, we map the cosmic web locally through large areas through these spectroscopic surveys like Sloan and now DESI coming up. And we'll want to do the same thing at higher redshift for the reasons that Charlotte's very greatly outlined in terms of trying to probe the morphology of ionization, trying to probe the formation of these incipient structures, these luminous structures, these protostars and protogalaxies coming out of the epoch of ionization, all the way through to cosmic noon or cosmic high noon. I don't know what the current term is, but we want to do that. And things like JWST are going to be really great at diving into individual objects, into some deep fields. But the field of view of JWST is measured in square arc minutes. And we'd like to have something that works at square degrees. And this is where line intensity mapping, sort of a more generalized idea of 21 centimeter tomography, can be a solution, because these experiments are not going after individual sources with some kind of target selection. Rather, we're trying to look into a spatial spectral field, some kind of co-moving volume, and we're trying to map out the fluctuations in the integrated line intensity in a given spectral line, be it 21 centimeter or be it some other line. So we're mapping intensities, not positions, just in 3 dimensions. And we want to get science out of that through some kind of summary statistics, be it the power spectrum, be it one-point statistics, be it cross correlations. And this will incorporate not just the contribution of the brightest sources, but also the clustering of fainter sources that may not be detectable in isolation in a conventional survey. And that will let us infer astrophysical and cosmological information, things like luminosity functions, things like cosmic densities of various quantities. And overall, we're getting the nature of the high redshift cosmic web, all of these kinds of things that happen across the filaments and peaks and light up this large-scale structure. So Charlotte talked a little bit about 21 centimeter tomography, which of course has been emerging for a while. However, in the past decade or so, another area that's seen a lot of interest is this niche in the middle here, which is trying to do intensity mapping with far infrared lines associated with obscured star formation. So lines like carbon monoxide, C2, which is singly ionized carbon. And so in particular, I work on a few of these experiments up top here. So one of the experiments I work on is COMAP, which is not going to be in this talk, but it is also eventually going to work towards ionization. You can talk to me offline if you're interested in that. But today I'll be talking more about this kind of experiment. Experiments like time at CCAT prime are going after the line intensity signal at redshift 6 to 8 towards the late end of ionization as these ionizing emitters start to emerge from neutral IGM. And of course, we can talk about 21 centimeter, we can talk about CO, we can talk about C2, but the fact is all of these are tracing the same structures. All of these are tracing the same cosmic web, especially at late times where you're not seeing the neutral IGM and things like H1. You know, you're seeing the same peaks, filaments, voids. These are redshift slices from a simulation that that's been, you know, the kind of simulation that we do at CETA, which are these approximate cosmological simulations. We can generate hundreds of thousands of them at once, but this is just one simulation and one slice of one simulation. You can see, you know, H1, CO, C2, these lines will illuminate the same cosmic web, sure, with different emphases on different parts, but ultimately it's independent probes of these kinds of structures through different baryon processes. This illustration is a bit deceptive because what we'll really observe is not this so much as something like this, because of course there's only so much angular resolution you can get at meter wave, centimeter wave, millimeter wave. But the fact stands, of course, that even with this kind of blurring, with this kind of confusion, we're still sensitive to the clustering at large scales, which is in turn sensitive to things that are going on at smaller scales. And I'd like to emphasize, of course, that right now we're really at the incipient end of a timeline, a roadmap that will eventually lead to very large line intensity mapping experiments. So this is a table from a white paper that was submitted to the SNOMAS process, which is why you have things like neutrino masses and dark energy constraints up there. But really, this roadmap applies more generally to all kinds of use cases. Right now, we're at this first stage where we're building pathfinders that are targeting initial detections. We'll move eventually towards the later end of this decade to intermediate stages that move beyond initial detections, really characterize the clustering of these line intensity fields. And then eventually, by the mid of the next decade, we'll be moving to CMB stage 4 sized spectroscopic focal planes that will really do cosmological line intensity mapping over very wide areas, hundreds, if not thousands of square degrees. So what's the target for the experiments that I'm talking about? The target for millimeter line intensity mapping experiments is this ionized carbon line, rest frame 158 micron C2 line. I'm showing a selection of redshift, low redshift infrared galaxies here just to show how bright the C2 line can be. It can be up to 0.1 to 1% of the total volumetric infrared luminosity. It's a very prominent cooling line. And it's also being used successfully already in surveys with things like ALMA to try and constrain, star formation activity at high redshift, late epoch organization, and individual sources. And you can see that there's this correlation on the right panel here. The x-axis is star formation rate, typically inferred from something like the volumetric infrared luminosity, and the y-axis is your C2 luminosity. And you can see across local galaxies, across high redshift galaxies, across simulations of high redshift galaxies, there's this consistent correlation in general between star formation and C2 luminosity. So basically, this makes it a very good complement to something like 21 centimeter, where we're really tracing the ionizing star-forming sources that are getting rid of the neutral IgM towards the end of ionization. And so, as I said, we're sort of at the first step here. There are a number of experiments that are trying to go after an initial detection of this C2 signal at redshift 6 to 8. I'm not really equipped to talk about Concerto. This is a French experiment running out of Apex in Chile. But I'll talk a little bit about the other two experiments because I am involved in both of these, just to get a sense of where these experiments stand and how close they are basically to fielding and taking data, which is a bit scary. So the first one is time. I've seen worse acronyms. It does make it a bit difficult to search for it, but this is a tomographic ionized carbon mapping experiment. This is very much geared towards an initial detection. The instrumentation is quite conservative. It's a waveguide grading spectrometer in front of an array of TESs. There's no, you're trying to minimize surprises. You're trying to minimize your tech development burden and your analysis burden. The initial survey is also somewhat conservative. It's a degree long by a beam wide. So you're really serving this 2.5 dimensional slice of redshift space over this sort of nominal 1,000-hour program. And at the end of that, you basically expect reasonably significant detections of the C2 power spectrum at redshift 6, redshift 7. So this experiment is progressing. We are going to operate from the Arizona Radio Observatory at KITP, where we've undergone some engineering runs already, including just this last winter. And we expect full science operations to begin later this year. In particular, we're already demonstrating, even with only a partially integrated instrument, some spectral imaging. Of course, we're not going immediately after the high redshift C2 signal, but the frequency band that we're working in is not just sensitive to high redshift C2, it's also sensitive to lower redshift CO, and so we can go after galactic sources for commissioning tests. And you can see that this false color image of the area surrounding Sagittarius A looks very orange. And that's just because that's the CO line emission. The CO line emission around the central molecular zone of our galaxy is very broad and very bright. And so we can go and mask those channels out, and you can recover the continuum clumps. So we're really truly demonstrating spectral imaging across many channels. And I think we're kind of the only C2 line intensity mapping experiment to do that at the moment. Looking a little bit beyond time, there's EOR spec on FEAST, which is part of the CCAP prime facility. And I think I've got all the acronyms in the right places. I think there are at least 2 people who can point out if I'm doing anything wrong. This is a sizable partnership between a number of American and German institutions. And the current focus is the construction of the Fred-Young submillimeter telescope, which is abbreviated as FEAST. This is going to be a telescope on a high site on Tor, very near the summit. And the high site, combined with the design of the telescope, which is low emissivity, large field of view design, optimizes this observatory for very fast mapping speeds across a very broad frequency range. And fortunately, one of the key programs of this observatory is going to be C2 line intensity mapping at the epoch organization. So this is going to be the Deep Spectroscopic Survey run with EOR spec. And this is a 4,000-hour program looking across 2 forest graduate fields. You can see that the survey design is a lot less conservative than something like time. And that's really enabled by the design of the instrument, which is going to be a much less conservative design in and of itself. But the upshot is basically, here's your forecasts for power spectrum of C2 at redshift 6. I can't seem to zoom in much further. Oh, there we go. And you can see that basically the FEAST survey will beat out current generation surveys like Concerto and Time by about an order of magnitude. And that's going to allow us to improve constraints on the existing models much better by about an order of magnitude. And it's really the high site, the low emissivity, the novel instrument design that's aiding us down the first steps on the path to this wide field line intensity mapping idea. So as we continue to progress in this experimental roadmap, what I'm trying to do is be ready for the data. I work on anticipating and implementing different kinds of line intensity mapping analyses. I've tried to anticipate what a cross correlation might look like between line intensity mapping data and cosmic shear data. I've tried to anticipate the use of the wavelength scattering transform. I've tried to anticipate the use of cross-correlation based filtering to try and improve the recovery of the C2 line intensity map itself from a line intensity mapping experiment in cross-correlation with other tracers at the same redshifts. But all of this work, you can throw all kinds of tools at this. You can throw peak patch simulations at this for large numbers of approximate cosmological realizations. But at the end of the day, what it really demands is some kind of framework for anticipating the signal. So this is where I return to this plot, because here, to simplify things, I was showing you the range of models. I can break it up into all the different papers that we were using for this CCAP time forecasting paper. And all of these models, in this particular case, connect C2 to star formation rate, which seems reasonable based on what I told you earlier. There is a reasonable empirical correlation between C2 and star formation rate. I'll go into why some of us either are starting to see it a different way. But the gist of it, right, is what's really important across these, designing all these models, trying to forecast analyses, trying to design future surveys. What's really important is the connection between your galaxy properties and your halo properties, your line intensity fluctuations to your matter fluctuations. What is the bias with which line intensity field traces the matter density field? Because that impacts your power spectrum, the clustering component of it, and what's at the center of that? It's the relation of the line luminosity to properties, for example, like the halo mass in a very simple sort of linear halo model. And of course, this is basically saying, if you have a line intensity field, how does that respond to the presence of your halo? So your galaxy halo connection, your response functions, that is everything to these kinds of analyses, trying to forecast for future surveys. So coming back to this C2 star formation rate, it is true that we empirically observed this relation, but the physical connection seems somewhat tenuous because C2, in fact, emerges from all kinds of different phases of the interstellar medium. It doesn't just arise from nearby to star-forming regions, it originates from the more diffuse neutral and ionized phases of the interstellar medium. So even though we observe this empirically, it's not clear what the physical connection is between these two variables. And then, of course, on top of that, if you want to use C2 as a star formation rate tracer, the proportionality between C2 and star formation rate, here represented by IR luminosity, actually evolves with IR luminosity along the x-axis here. So it's not really clear that this is a connection that's on solid ground. So I'm showing a photo of Li Chen here, Li Chen Liang, who's a postdoc at CETA, and he has been thinking a lot about C2 using these fire simulations, feedback in realistic environments. These are zoom-in galaxy simulations incorporating hydro, incorporating lots of different feedback prescriptions. And so as an example here, I'm showing you the snapshot of a fire galaxy at redshift 6, in optical basically, and then the middle panel here in C2 surface density, and then on the right hand here, the interstellar radiation field. And you can see, right, the C2 isn't just coming from regions of star formation, it's coming from everywhere across this mess of a galaxy. And what's really going on is not that C2 is dominated by contribution from photon-dominated regions, it's really that the C2 is coming from the interplay between the interstellar radiation field and the diffuse parts of the interstellar medium. That is the dominant contribution. That is what Li Chen has found by looking at these fire sims at small scales. And we can go ahead and translate that into some kind of halo model that we can apply to these approximate cosmological simulations. Basically, we make some kind of simplifying assumption that basically the C2 luminosity is modulated by the H1 mass as a proxy for the amount of diffuse gas that can emit in C2 and the gas phase metallicity. And we can formulate a corresponding halo model going from the halo properties to various intermediate galaxy properties, leading us eventually back to the C2 luminosity, the thing that we really want. And so Li Chen and I and Patrick Orleville, who's an undergraduate who recently finished at McGill, we've been working on basically putting all these ingredients together into a new model for this kind of C2 line intensity signal. So this is still preliminary stages, but if you throw this model at a peak patch simulation, for example, we basically recover the same kind of C2 deficit, the evolution of proportionality with IR luminosity that we see in fire galaxies. And of course, we can make a power spectrum prediction out of it and put it on top of all our other models. Of course, I wouldn't put too much stock into the normalization quite yet, because, of course, you can say we know the modulating factors, but the normalization, of course, is the thing that we will try to constrain, really, with this kind of line intensity mapping experiment. For example, you can go looking for other examples of people thinking about C2 as a tracer of H1 mass in galaxies, in particular a set of papers from Caspar Heinz. And what Caspar Heinz tries to do in particular is look at these gamma ray bursts, trying to constrain the overall normalization. You can see, of course, these gamma ray bursts, the resulting plot, points on the figure here, they sort of have a sizable scatter and sizable error bars. So you can imagine if this normalization went up by a factor of a few, the prediction of the power spectrum might go up by a factor of 10. And then, of course, there's still a lot of work left to do in terms of we understand what the average relation should be between the galaxy properties and the halo properties, but there is some kind of extra ingredient, which is the environment of these halos, and that is something we'll be looking to try and really probe with these peak patch simulations, looking at the field information surrounding the halos. So I'm pretty much done, but just to really emphatically reemphasize that line intensity mapping is a direct observation of the multi-scale cosmic web. It's serving the large-scale structure as lit up by all these small-scale baryonic physics. The experimental progress is really picking up. We've got a number of instruments coming up in the next few years. Time is set. Science start date is going to be later this year. The construction is really proceeding. First light is supposed to be 2024, and EOR spec will come up within a year of that. But as we get this experimental progress, it's really important to get the theoretical framework in place. Getting the galaxy halo connection right as much as possible is really key, and it's going to require interaction across all scales of astrophysicists. And CETA in particular has been very handy for that because we have a concentration of various expertises that has come together for this project that I was talking about. So I'll just leave it there. Thanks very much.
Thanks for a nice talk. I have two questions. So one is, could you say a little bit more about how you remove foreground CO line emission from other sources?
Yeah.
And then the other question, or I'll let you answer that one first. Go ahead.
Oh, so I don't have slides prepared for this, but yes, so there is lower redshift CO emission. As you saw, we're kind of exploiting that for our commissioning tests, but when it comes to trying to get the EORC2 signal, that's going to be a nuisance. One of the ways we want to try and mitigate the CO foregrounds is things like targeted masking. We'll try and overlap with areas where there's lots of galaxy survey data coming from redshift 0 to 2-ish, and we'll mask areas where we anticipate significant CO foreground emission, and that will tamp down the emission significantly. We can also think about in future, as we enhance the spectral resolution of these instruments, we can think about exploiting anisotropic effects, projection effects, try and distinguish the CO from the C2. One other thing I was thinking about is basically filtering the C2 map based on cross correlations with other tracers. So you can see, for example, the signal here is on the top left panel. The signal plus integral over lines is on the middle top panel. It's a mess, right? Doesn't really resemble the original signal at all. And then you add on the noise, and it just becomes even worse. So a Wiener filter reconstruction, for example, would not recover the signal or the integral over lines. But you can try and do covariance-based filtering against, like say, a Lyman alpha emitter catalog that's in the same volume. And you can try and recover the original signal a lot better that way. So lots of different strategies. And I think there's a lot of promise in being able to get past this problem.
Right, but if you have another tracer in the same cosmic volume, right, and you want to do cosmology, wouldn't you just use the other tracer?
Yeah, it depends on what you want to do, because the Lyman alpha emitters are really going to be tracing unobscured star formation principally, and the C2 is going to be tracing obscured star formation. This is one of the motivations behind using all of these different lines, the H1, the COC2, and all these rest-frame optical lines.
Got it. Okay, and then the other question is, I was intrigued by your theoretical work on the C2 deficit, and I was wondering, you reproduced the deficit, but you didn't say what the physical explanation for the deficit was. So I was just wondering if you have an interpretation there.
Yeah, so it's really a saturation of different factors here. At some point, you just run out of excuse me. So it really comes down to the physics of the metallicity of the gas relative to the amount of gas that there is. In different regimes, you have situations where the C2 luminosity is sensitive differently to these different factors. I don't quite have the presence of mind right now to give you a really detailed overview of everything, but Li Chen's paper really goes into all the physical insights that he's gained from looking at the fire sims for that.
Hi. Thanks, Dongwoo. That was really nice. I particularly enjoyed the second part, which almost answered the question that I had, which is the same question that I asked the Chime people, which is when you first detect this thing, what are you learning? So you will get the normalization before you get anything else. And that better be interesting because you're going to write papers on it, right?
Yeah.
So what combination of things will that tell you first?
So at first we thought it was going to be a combination of things like the C2 luminosity function with the star formation rate density. You have a point there, redshift 6. This is how much star formation rate is going on average. Now we're a little less certain because now we're thinking maybe SFR isn't the thing to associate it with. Maybe it's the gas mass. And so I think that's one of the reasons why we really need these theoretical outlook in place, because I think that's a really valid question. We still have a ways to go to fully understand the science that we're going to get out of that normalization of the power spectrum.
Thanks.
Yeah, I guess I had another question about the power spectrum. It seemed like your new model had quite a different scale dependence. as well as the normalization. I wonder if you could explain why that is.
So one of the reasons is the different prescription of stochasticity in the C2 luminosity. So for example, a lot of these other, I didn't need to scroll back, all the models are there. But a lot of these other models, they prescribe a certain amount of, duty cycle in the C2 emissions or some kind of scatter around the average relation. And that is going to contribute to the Poissonian noise that you get in the Paris spectrum. We are still playing around with the prescription of stochasticity in our current model. So I definitely wouldn't trust this shape dependence too much, the high K points. But that is also something as well where we're ultimately hoping to incorporate environmental information to try and better inform these modulating factors for the luminosity in a given halo.
Are there any other questions? Yeah.
Earlier on, you showed a prediction. I think it was for time. You had the observed and then the true. Yeah, there's a huge difference between the true and the observed. It looked like the modeling must be
it's a projection effect, because
awesome.
what's shown there is basically, so this is not an actual observation, this is the anticipated observation. And it's because of the way time is trying to do a 2.5 dimensional slice. So one transverse dimension and one line of sight dimension versus two transverse dimensions. So what we really observe is this projected P of K versus the actual spherically averaged P of K. And that leads to a different normalization as a function of weight number. Otherwise, these models are interchangeable. They're the same. It's the same C2 model under the same assumptions, but it's just different, slightly different observables.
All right, we have time for one quick question, and the other speaker should come in and set up. No? So I have one. You use the fire simulations to try to guess the to have the C2 emission from them. How do you think the results that you obtain from that are dependent on the detailed chemistry model that goes into the simulations and the assumptions?
It's a very interesting point. I think the chemistry is fortunately not as complex as something like CO, which obviously I didn't talk about, where the CO, you have to really worry about things like photodissociation and shielding from dust versus H2 and things like that. So I think there's there's less physical complications along those veins. However, it's something where we definitely want to see the effects of different kinds of chemistry codes, different kinds of assumptions along about those chains of reactions and dissociations and what have you. I thought we were going to ask about the impact of different feedback mechanisms, really, but
that's another.
That's a whole other kettle of worms.
Okay, thank you.
Yeah.
Well, let's thank Dongwoo again.